Good afternoon, everyone. How are you guys doing? Doing all right? I'm just checking my mics now. I have two mics.
Two mics?
Yeah, because there is another camera over there. We'll see how that works.
Oh, whoa.
And if that works better than what I have right now, then I'll keep on using that one. Okay, so we have a lot to cover before the exam on Monday next. So I hope you remember that. And that's what we agree on. It's a little bit early, but we agreed on that, and then we're going to stick to it. Okay, so today we're going to start talking about fluid-driven fractures. Fluid-driven fractures or hydraulic fractures. And in order to do that, we'll start by talking about the wellbore environment and how a fracture grows out of a wellbore. These equations you already know, and we're just going to apply that to see how a hydraulic fracture will grow out of that. All right, so let's do that. Let's imagine a vertical wellbore. This could be also a perforation. It's the same thing, just a different scale. And let's say that we are under normal faulting condition. Again, you can extend this to other conditions later on. We'll say that the minimum principal stress goes in this direction. Maximum horizontal stress like that, and vertical it is like this. I'll make it a little bit thicker just to mean that that one is higher than the other two, and I'll make this one also a little bit shorter. Okay. If you remember from the equations from Kirsch, for stresses around the wellbore, we will write those equations and we obtain that sigma theta theta at the wall of the wellbore for any angle was equal to this. I'm just copying the V and the minus H mean minus sigma H mean cosine of 2 theta. Theta is the sigma H max at whatever you look at. For example, here is going to be theta. Okay, so you can find in my notes, which is reviewing that, but this comes out of the long equation of Kirsch, in which now we just set to find the stress of the wellbore, and we are interested in finding the point of lowest stress around. And if you remember, that's going to be for theta either equal to 0 or equal to 180 degrees. So somewhere over here, I'm going to have tensile fractures if I increase the pressure enough in the wellbore. And that's because orientation of the stresses. All right, so I'm going to use the previous equation, which is this one, with these two conditions, either 0 or 180 degrees, which will be over here. And I'm also going to say that the hoop stress is going to reach the value of the tensile strength. If you have a tensile strength in the rock of 1,000 psi, well, the stress at that point is going to be negative 1000 psi in tension. And if we do that, basically by replacing the hoop stress by the tensile strength and making this cosine of 0 or 360, here we get just, if this is cosine of 0 is 1, and cosine of 360 is going to be 1 as well. So we just have to add this term, and when I put all of this equation as a function of PW, this is going to be something like this. PW, I just get it out of here. I'm going to call that pressure, and I move the pore pressure on the other side together with this value, which is going to be now tensile strength, and I'm going to get this equation. And this is what is called breakdown pressure. And this to get the rock to fail in tension. Okay. Just a short reminder. If we are talking in terms of normal stress and shear stress, the limiting state of stress without considering a yield cap imposed by shear and by tension. When for you get to, let's say that this is your state of pressure on the wellbore. If you increase the hoop stresses too much on one direction and lower it in the other, you can take the Moore circle to this new condition, and when it does that, you're going to have a failure in shear, and this is what the fractures look like. If you take the state of stress into tension, just the sides have to be in tension, not two of them, that failure is going to be like this, with the plane of the failure perpendicular to the applied tension. Two types of fractures, one in shear, another in tension. Okay, so let's use now this equation in order to predict what will be the breakdown pressure, but we're going to simplify it a little bit. I just want you for now to notice that this breakdown pressure depends on pore pressure. The pressure in the wellbore has to be higher than the pore pressure. That's the only way that a fluid is going to be able to apply a stress on normal stress in the pore of the wellbore. The second factor is stress and isotropy, which means the going to be actually the wellbore, and this one is the tensile strength, which makes a lot of sense that the higher the tensile strength, the higher is going to be to fracture. So assume for the moment life easier that sigma h max is about the same as sigma h min, and let's just call it sigma h. Of isotropic stresses is in the. If we do that, then our equation of breakdown pressure is going to simplify, and this is going to be equal to the pore pressure plus sigma h max and sigma h min are going to be the same. So 3 minus 1 is just going to be 2 sigma h plus the. Okay, so this is going to be case number 1. Just in an extreme of isotropy. You remember, if we were considering shear failure, effective stress as a function of what would be the maximum effective stress as a function of the least effective stress. Much higher. Okay, we didn't put a lot of emphasis on this in our class, but failure also going to stress that you have in the surface. Basically, place in which we have a tectonic strain, the maximum stress that you can have in this place is going to depend eventually on the equilibrium of faults. And for example, if I have SA stress regime, what the equilibrium of failure or the equilibrium of fault would tell me is that the maximum friction for reverse faulting. For normal faulting, it's similar, but now sigma 3 is going to be sigma h min, sigma 1 is going to be sigma v, and the strike slip is going to be and sigma h min, correct. So then for the case of extreme and you remember for a friction angle is this. So let's say this is equal to 3 sigma h min. And be a case which is anisotropic in terms of stresses. In that case, V is going to be if I replace sigma x by 3 sigma h min, telling you is that when you have high anisotropy, the only thing that is going to help you have it higher in your wellbore is the tensile strength of the rock. And eventually, you didn't have any tensile strength in the rock. As soon as you get to the pore pressure, likely to start opening a hydraulic fracture. Okay, so this equation is just to tell you where and when a tensile fracture like this one and like this one over here would initiate around the wellbore. And this is going to help us to get started with analyzing hydraulic fractures. Okay. So let's use number 1, and we'll see what the leak-off test looks like. Are you guys familiar with the leak-off test? Yes? Raise your hand if you are. Half of you. Okay. In a leak-off test, you basically, let me write first the name. And it's going to be the same thing that we're going to talk about is going to apply to the diagnostic fracture initiation test. Basically, this one is done for drilling applications. This one is done for hydraulic fracturing and for completion. But the mechanics is very similar. But let's talk about the leak-off test, and then we'll extend that to the diagnostic fracture initiation test or the defeat test. All right, so in this test, we basically pressurize a cavity, the rock, with a fluid. In the case of the leak-off test, you pressurize the entire wellbore. You get to a certain depth. After that depth, you run your casing, you cement it, you put a packer in a section, and then you inject the fluid at a given injection rate, which is going to modify the pressure in this cavity. In the case of the leak-off test, again, this is for drilling, and you pressurize. In the case of the defeat test, you may pressurize a small section of the wellbore, or sometimes you also may pressurize a case wellbore with perforations. But it's a similar thing. You're just pressurizing the rock with a fluid. Okay. Then what we're going to do is we're going to inject a fluid, which in the case of the leak-off test is going to be drilling mud, but in the case of the defeat test, it's just going to be a fracturing fluid. And we're going to inject this such that we're going to increase this quickly and then keep it constant for some time. And as we do that, we're going to measure the pressure in the wellbore. Okay, let's do the case for isotropy in which we say sigma H max is equal to sigma H min, and also this is the minimum principal stress. Objective is to see how pressure is going to vary as we are injecting this fluid and we form at the beginning a tensile fracture and later a large hydraulic fracture. And we know the equation for how to start with, and this is going to serve as a motivation about how to continue. All right, so if you look at that equation, it tells us that the maximum pressure in the wellbore, PV, is going to depend on these three things: pore pressure, far field stress, effective stress, and tensile strength. So let's start with the pore pressure. Let's say the pore pressure, it is somewhere over here. Let's say that the minimum principal stress is somewhere over there. So this is the minimum principal stress. Then the distance from here to here should be 1 sigma. And if I add another sigma h, that's going to be 1 more sigma h. So now I have 2 sigma h. And I'm going to add further tensile strength. So according to my equation, this is going to be PV, at least as here. So we start this process of injection. Let's say that at the beginning, the pressure in the wellbore, it is somewhere over here. That's what starts large, and then we start injecting. This is into the rock, but it is more or less sense that nothing is going to go through here. You start injecting. What's going to happen with the pressure? It will increase, and will it increase? It will reach a maximum value. Maximum value, as we were saying before, is going to depend on this equation. So and when it's healing, it will cap how to right now, but we know at this point of this well, what's going on when I get and then if I continue increasing pressure, this is going to grow, and pressure, it will reach a peak. But now the question is, what do you think? It will continue at that pressure, or it will go down? Why would it go down? Okay. Diffuse? Yes, I think what you're saying is correct, but let's imagine for a moment that this is a low permeability rock. So there is very little that gets into the rock. As you open the fracture, that's going to create a very high permeability path for the fluid to flow. And in general, what is going to happen is that as you open this new path, and if you keep injecting always at the same rate, the pressure is going to go down in order to equilibrate with the amount of fluid that goes into the fracture. At the beginning, also, the fracture opens up very quickly, and as that fracture opens, it will take quite a bit of volume that goes of drilling mud or fracturing fluid to go into the fracture until it gets filled, and then it starts to propagate. So you open a new volume, and all the fluid until the fluid at the given injection rate catches up with how fast the volume or the fracture is opening. This one is going to decrease. The question is, how far is it going to decrease? And what is that value? Well, you're getting too fast to that point. we are still injecting at the constant injection rate. So notice that this is the minimum. This is the lowest stress that you need to open a hydraulic fracture. But that doesn't mean necessarily that your fracture is going to be. In order to have the fracture propagating, you need some additional pressure. And this additional, the difference between the minimum principal stress and the pressure in the wellbore or the pressure in the fracture is what is called net pressure. So in this particular case, net pressure is going to be PW minus S3. In general, is the pressure in the fracture minus the minimum principal stress. You need some pressure in order for the fracture to propagate, in order to make the fluid go through the fracture, and in order for the fracture to keep the fracture open. And this is what we're going to see right after we finish with this. What is this value of net pressure? How we can calculate that one? We know this one. Now we want to calculate that one. Okay. As long as we keep injecting pressure, which is called the fracture propagation pressure, stay more or less constant. Sometimes it increases, sometimes it decreases. Depends on the geometry of the fracture. But let's say for now, we'll say it stays constant. And point, we're going to shut in the injection, and then what you would expect is that after you go down, because you're now the pressure should, first of all, it goes down because you're not injecting anymore, and second, it will go down because the fluid is also infiltrating into the rock, and it's going to go as low as the pore pressure. As instant time shutting pressure. Let me continue my sketches over here. Propagating. Fluid that is going from the wellbore into the fracture, leak off that goes from the wellbore to the rock, and from the fracture at the fracture it was in the fracture is going to filtrate into the rock. That's why the pressure. There is really a point, as Jack was saying, that the fracture is, and at that point, the net pressure is not going to be positive anymore. But now, since the fracture is now closed, that means that the net pressure is going to be 0, and the fracture closure pressure is closed. Now there is just, we assume a fracture activity is fluid leak off just from the wellbore. There are methods in order to pick this fracture closure pressure. I encourage you to go to my notes online if you want to see that. Basically, what you use here is the square root of time method in order to see where this point is. And when there is a change from linear fluid flow, assuming that the fracture is a line and there is leak off from this entire line, and when that changes, this is the fracture, to just a point source, if you plot the decrease of pressure with time as a function of the square root of time, you'll be able to see where that point is. And if you do that, you will be able to calculate the fracture closure pressure. But for now, what I like that you remember from this is that we know more or less what the breakdown pressure is going to be, but this new thing that we have right now for the propagating pressure is going to be the net pressure. And that's what we want to calculate now, at least to have some idea. What the pressure will look like as a function of time. If you had a case now with sigma H max equal to high anisotropy, and if we do this again, if somewhere over here, this is the pore pressure, and this is time, and let's say this one is sigma H, but your tensile strength is actually over here. What this equation now is telling us is that the breakdown pressure will be just pore pressure plus tensile strength. So you're just going to go up to here, same rock, just different stress, and in order for that fracture to continue propagating, you will have to go over to some limit, and then it will propagate with a given net pressure. But the big difference is going to be that before this one go over a hump and then go into propagation pressure, this one goes directly into that regime because you don't have to overcome the near wellbore stresses, or sometimes called also stress cage around the wellbore. The presence of the wellbore makes the stresses vary around the wellbore, and if you have an isotropic state of stress, that's the case in which stresses are going to amplify the most, and you have to increase the most the pressure. Some stress and isotropy is going to be a lot easier to actually. Again, in order to have a fracture propagating in time, you have a net pressure which is positive. Okay, so let's try to context of vertical and horizontal wellbores. And let's see how now those small drilling-induced tensile fractures will grow into a large hydraulic fracture. So let's say that we go to a place in which you drill a wellbore, and then you fracture that wellbore, and let's say that there is a target formation somewhere over here that it's meant to be fractured. Now let me put the shading in the other direction. Okay, so let's add to this a coordinate system. Let's add to the condition. We're going to say that this one is normal faulting. And all right, and then we're going to start making some calls. Let me zoom in a little bit more. All right, case number one. Vertical wellbore. And let me add what the stresses are. In this direction we have sigma h min. In this direction we have sigma h max. And I'm considering this location over here. So that's going to be the vertical, which is going to be larger than the other two. In this location, and you start, let's say, pressurizing this section in the page with the wellbore, this is going to look something like this. Case number one. Around the wellbore. You can do that because you know what is the north, you know what is the east. So we're looking at the wellbore in 3 dimensions. So what did you say, David? East-west. So these drill-induced tensile fractures are going to happen somewhere over here and somewhere over there. Like this. If you remember, same as just following the previous drawing, tensile fractures in the continue to grow. How do you think they will grow? Remember that our principle fracture or an open mode fracture open as a plane perpendicular to the least principal stress. So it's going to keep on the same plane, right? So, and let's assume that the fracture is limited, fracture height is limited to this height. So it's just going to continue opening like that in the same plane of the tensile fracture at the wellbore. And if we put this into our formation over here, that means that you could, if you start a fracture somewhere over here, it will just keep on growing on the same plane perpendicular to SH min. So in this case, if this is a vertical wellbore and you pressurize an open hole completion, that's what you would expect as a hydraulic fracture. Go to let's go to case number 2. In case number 2, now we drill a wellbore out of here, and then we kick lateral into this direction, in direction east-west. If we make a zoom out of that wellbore, and I'm going to do it down here, this is going to look like this. This is a section of the lateral, and remember that minimum principal stress is in this direction, that this is normal faulting, so vertical stress is going to be in this direction, and SH max is going to be in this direction. Same question. Pressurize this wellbore. There's no casing, there is nothing. Where would the fractures start? The tensile fractures. Why above and below? Yes. So I'm going to make this a little bit easier. Let's imagine that this is a cross section of the wellbore there at that position. So you're right, Stefan, but why?
Oh, why?
Yeah. Well, but you're answering the second part. But the first part, it has to do with the distribution of stresses around a wellbore. So in this case, for example, we have these tensile fractures in east-west because if I do the same thing as I did before, notice that this is SH max and this one is SH mean. Therefore, the maximum compression is going to be here, the tension is going to be there because this one is different than that one. Well, the same thing over here, we're assuming that this is normal and that SH max. And again, if we extend this in 3D, this will look like these planes around the wellbore. And if we keep on increasing the pressure, these ones are going to grow, and the same as before, they're going to grow per principal stress because that's the most energetically savvy way of propagating. Yes, Jack, you have a question?
Yes, so earlier you mentioned is because of SB as shouldn't be within isolation for that thing.
So what is your question again?
Because in the above case with SH max and SH minimum on that plane, so in the below case should be SB and SH minimum, right? Because
Correct. Yes. So SV, if I look just at this plane, is here, and SH mean is there.
yeah, okay.
And Then let's get this case again to now this block diagram. If you were to start fractures in this wellbore, and if it is open hole, let's say the entire lateral is open hole, probably you will start the fracture somewhere over here, and this will just grow. And let's assume that the height is limited by the pay into a hydraulic fracture, which is perpendicular, and it is in this location. And even if you have several perforations, and if you have startings at different points, eventually this all will just join in one large plane, because all these small fractures maybe are going to be aligned and later just going to coalesce in the same plane. Yes, Stephanie?
Do fractures longer up direction than down direction, or
On many things. And we're going to this. We'll talk about fracture height, but it depends on the properties of the rock, and it depends a lot on how horizontal stress varies with depth. If you remember from, I think it was the first project that we worked with, we look at variation of stress with depth, and we look for kind of a sweet spot where the hydraulic fracture would stay, because that was the local minimum of the horizontal stress. So it's going to depend on that, and usually they tend to grow up rather than to grow down. But again, it depends on the profile of stress and the properties of the rock. Okay, so we have number one, we have number two. Let's work with another option over here, and this is going to be a wellbore that goes into the pay zone again, but now goes in direction north. And our objective is what's going to happen with the growth of a tensile fracture. Okay, let's start with that. We'll make a schematic of this wellbore. And now in this plane perpendicular to the wellbore, I'm going to have SV, and on perpendicular to it, I'm going to have SH mean, and this direction, SH max. Where would the tensile fractures start? Top and bottom or on the sides? So let's forget about this one. We have to look at which one is there. It's going to be top and bottom. Stress is in the direction of the circumference. So the local principal stress, according to Kirsch, sometimes a little bit more complex. You have to see if that stress is actually lower than this one, than that sigma h mean. But let's assume for a moment that the sigma 3 is actually going in this direction, east-west. Okay, if this is the case, then what this is telling me is that these short tensile fractures at the wall of the wellbore are going to grow like planes which have a strike north-south 90 degrees and are perpendicular to the local principal stress, which is sigma 3 in here, but it is not the far field least principal stress. So one goes north-south, the other one goes east-west, the other one goes north-south. So what do you think will happen to this tensile fracture as it continues growing? Do you remember how far the influence of the wellbore goes in affecting stresses? That was project number 3 or something like that. Anyone remembers?
Is it on the order of like tens of centimeters outside of the wellbore?
It depends on the radius of the wellbore. The bigger the wellbore, the bigger the influence, but in relative terms, it's just like 1 diameter to 2 diameters maximum. Further away, there is almost no effect. The rock doesn't know at all that the wellbore is there. But close to the wellbore, it does. So while locally this might be the minimum principal stress, up here, the minimum principal stress there is going to be this one. And that's going to be the direction. So what is going to happen, ideally, this might get a little more complex in reality, is that this fracture is going to rotate and look something like this, where, let me see if I can get this effect. I'm meaning here that this top lobe is perpendicular to minimum principal stress. Let me see if I get this one a little bit better. This is going to start somewhere over here. It's going to be something like this. While this surface starts perpendicular to the local minimum principal stress, as it gets further away, the plane is going to be perpendicular to sigma h mean. You kind of see that? Let me explain this with these 2 pages. So, close to the wellbore, start like this. But then, as it gets further away, it rotates and it's like that. So close to the wellbore, we have the near wellbore stresses that can make that local stress to be actually in this direction, but you get further away and this rotates. Well, the question now is that good in terms of completion? You want to make a hydraulic fracture in the field that looks like that. Why not, Joseph?
It's because you're not gonna.
Yeah. It's not only the shape which is weird, which is doesn't favor maximum specific area, but it's also kind of choking. That's what you want to say, Stephanie? So your fracturing fluid is kind of choking there. If you have propants, those are going to screen out at that point. In reality, it's not going to be exactly like this, but it's going to be a complex fracture that at some point has to turn. And when that happens, that's not going to be good for the fracturing fluids or for the propant. So this is not good. And actually, in order for the fracture to grow and to go through these points of high fracture complexity, fracturing pressure that you're going to need also is going to be a lot higher if you didn't have that. So what do you do in order to avoid this kind of tortuosity near the wellbore?
Can you go ahead?
Well, actually, but look, if you change direction, you're going to end up with something like that.
What if you went
And our objective here is to have multiple stages.
and increase connectivity between your crack, right?
Not. That's another topic, but let's assume for now it is ideal fracture propagation. So, again, this would be if you have it open hole, right? Let's say that we case it. And then we make perforations. These perforations are going to be holes into the rock that are going to collect fluid. Now, when you pressurize this case section and you go through the perforations, notice the orientation of the perforations. It's equal to this one, and it's equal to that one. And in those, when you start pressurizing the perforations, then your tensile fractures are going to be perforation located at these two regions. And now, if your hydraulic fracture continues to grow, it's just going to continue on that plane. So by having these perforations, now hydraulic fracture that may start something like this, it might grow into a large hydraulic fracture plane, which is perpendicular to the minimum principal stress. And if we take this into here, now assuming that we have perforations, we're going to obtain fractures that probably start like this, and then just assuming that these limits to the Poisson are going to grow like that. And our objective, as I was saying before, is to have multiple fractures. So we're going to have another one over here, another one over there, another one over there, and here our objective is to maximize surface area of the fracture in contact with the reservoir. Notice that almost in the same length of wellbore, while here I have 4 fractures, here I just have 1. So this is going to be a lot more of surface area in contact with the wellbore. Okay, let me finish this with some of these small fractures.
So can we
Yes.
Unless it's cracked. Otherwise, you're going to have a very bad simulation. Is that the like general rule?
The general rule is always here to have a wellbore which is perpendicular to the minimum principal stress. So that, like in this case, you have multiple fractures which are all perpendicular to the minimum principal stress. In normal faulting and strike slip, horizontal, but in faulting that's not going to work. Your minimum principal stress is vertical. So in some of those cases, you may need, if the pay is thick enough, you could do just a vertical weld. Okay, let's see how we have a few more minutes. Yes, Jack, go ahead.
So when you have casing and you do conversion, is the analogous to the first example we did?
Yes, like those, like the perforations are like small wellbores. And that's what they're going to serve to. They're going to connect the rock with the fracturing fluids, and they're going to serve to help the hydraulic fractures to grow more easily out of the wellbore. Take advantage of an isotropy of stresses of these near wellbore effects or near cavity effects in order to propagate the fracture in the plane perpendicular to the minimum principal stress. Okay, so we're going to come back to this multi-stage hydraulic fracturing. Later we'll talk about what is the length between stages that you need, the length between horizontal wellbores that you need for that. But for now, there is one more thing that we need to address before we go into that direction, and it is to answer what I was telling you before. What is the net pressure? So we know now where the fractures will, how they will grow out of the wellbore. Let's see what this net pressure is going to be. And we'll talk also later about fracture height. Okay, this is what I called the coupled fracture problem. And probably I should add here fluid-driven fracture problem. For this part, I follow a book which is a little bit old, but it's very good, about the mechanics of hydraulic fractures. It's called, actually it's called Hydraulic Fracture Mechanics. And in essence, what a few chapters of this book tell you is that the net pressure, defined as the pressure, let me put it in line, the pressure in the fracture minus the pore pressure, minus the minimum principal stress, is going to depend basically on three things. First, there's going to be a component of opening the fracture, which is going to be a function of the elastic properties of the rock. Basically, in this first step, And also, to make it simpler, we're going to assume that we already have a pre-existing fracture, let's say with 0 thickness. I'm looking at the cross-section of that. So in order to open this fracture, this is an elastic medium, and since it is elastic and infinitely long in these two directions, in order to open a fracture, you really need to move the solid up and down. And this is going to look something like this. And the pressure here in the fracture needed to do this. Part of this is going to depend on how elastic the rock is. This rock is going to have a given, let's say, Young modulus that we'll see in a bit why we'll call it, it's another type of Young modulus called plane strain modulus. And the stiffer the rock, the higher the net pressure is going to be in order to that open that fracture. So how much it opens, that's going to be the width, and will depend on the variable x, where x starts here, and that's y. And the value of the width is going to be proportional to, inversely proportional to the Young modulus. So soft rocks, easier to open a cavity, a planar cavity or a fracture. Stiff rock is more difficult. This part, and in order to solve this, what you will have to do is exactly what you did in project number 6 or method. You found what will be the pressure needed to open a planar fracture. If you set the pressure, right? Yeah, now I remember. So you set the pressure, and then you get the displacement. Displacement is basically the fracture aperture. So the higher the pressure, the higher the displacement, the stiffer the rock, the lower the displacement. In summary, in order to solve what is this displacement as a function of the net pressure, what you have to do here is just to solve a problem of elasticity. And you know, if we just want to make it simple, we'll do just, this is going to be, as we know, equations of constitutive equations. You put this together with equilibrium equation and plus this kinematic equation. You solve all of that, you get what is the displacement as a function of pressure for this shape. Analytically, we're going to see one equation that allows us to solve this. In general, you know the pressure, and you can predict what is the displacement, and therefore that's what you're going to get for this fracture. Displacement as a function of net pressure and the elastic properties of the rock. Okay, this is just one part. In order to keep the fracture open, you need pressure. Second, you need to circulate fluids through the fracture and also from the fracture into the rock. So let's imagine that this is a fracture, half wing of a fracture. You have fluid that goes through the fracture. you could assume something very simplistic, but still more or less accurate, like fluid flow between two planar surfaces. If you remember that in a transport class, you can solve what is going to be the flow rate for lambda, and this is going to be, I don't remember, I think, well, I would need some coefficients here, some numbers, but forget about the numbers. I'm just interested on what are the governing parameters here. The flow rate is going to be proportional to the width. The bigger the width of the fracture, the more I can move through the fracture. And actually, this depends on the cube of the fracture. How much it extends the direction perpendicular to the paper. We'll talk more about that later on. The higher the harder the fracture. And more for fluid to move. Pressure what? Pressure gradient, very well. So this is going to be the pressure of the fluid as a function of distance divided that distance. So I'm assuming that here x is in this direction. Pressure is not going to be the same here than there. In order to move, the pressure has to be here larger than at the end. So the pressure actually is not going to be constant in the general case, but it's going to have a gradient, because otherwise you don't have fluid flow. Okay. You have viscosity here. That means that you have viscous losses. Some of these fractures, they might be less than quarter of an inch for several hundreds of feet long. So these are relatively narrow fractures. In order to have fluids to move through, you require quite a bit of pressure in order to move the fluid. And this is just one part of the viscous losses. In addition, you're going to have leak-off. And the leak-off is going to be proportional to the permeability of the rock, inversely proportional to the viscosity of the fluid, and also is going to be between the pore pressure and the pressure in the fracture. But this is just one additional loss that you have to consider. So you not only need pressure in order to move the fluid through the fracture, you also need pressure, or you need to overcome this viscous loss inside the rock itself. Something very useful to do in order to think about this process of fluid-driven fracture is that how is the energy spent in propagating a fracture? When you do a fracture, you have a pump on the surface, usually with several of horsepowers, so that's energy. Where does the energy go? Okay, energy goes into opening the fracture. This is elastic energy. When you deform a solid and takes more stress than before, that goes into elastic energy. When you make fluids flow into a fracture and inside the porous medium, that's going to dissipate as a viscous loss. And you're also going to need some energy in order to do that. And last, there's going to be one more.
I'm sorry, what's Q again?
Q is the flow rate in the fracture. HF of the hydraulic fracture. Yes, yes. It depends how you do this, but generally, if you wanted to solve this problem, you will break this into small segments, and when you write your continuity equation, you have a sink term that takes into account the leak off. Okay, so let's see where I was. Okay, there is one more thing that we have to take into account. So we know that we need to open the fracture. We know that there are going to be fluids that flow. So we have forgotten about something. Anyone? Fracture length, we're going to see later on that, but that's related to this part of the problem and also to this one too. But in general, the longer the fracture, the lower the pressure that you need to open a fracture. But it's something else. We actually started talking about that. The strength of the rock. Very well. We started this talk saying that the rock would fail in as you have fracture propagate, the fracture is going to be breaking the rock unless it's going through a natural fracture, something like that, right? But let's assume this is a rock with no fractures. So here at the tip, you need to create new rock surface. And this is basically just breaking the rock. You need energy in order to break the rock. And that new rock surface, let's make a zoom. This is a fracture. We're looking at stresses at the tip of the fracture. As this one propagates, this is how the rock is going to break. We're going to have here, let's say, if I had an element of rock very close to the fracture face, I'm going to have compression because the fluid is pressing against. However, when I get to the tip, all of these forces going into this direction, pushing against the rock, are going to cause this rock, instead of being in compression, to be in tension at the tip. And that's what is going to make propagation. Because our equations of linear elastic fracture mechanics, they're going to predict that infinity. So instead of using a criteria, use something else, which is the fracture intensity coefficient, and we're going to say that when the fracture intensity in mode number 1, and this is a Roman 1, is larger than the critical fracture intensity, or also called fracture toughness, then the fracture propagates when the fracture intensity is less than toughness value, the fracture does not propagate. Again, this is toughness, and it is a property of the rock. And this is intensity, and it's a function of the length of the fracture, the net pressure, and I think that's everything. Let me check if I forget anything. No, at least for ideal conditions, or at least for a fracture with constant pressure, that's it. So this is what you impose, or this is the variable, this is what the rock has. And in order, again, to propagate a fracture, the intensity value is going to have to be will not propagate. Oh, well, that's another thing. You're getting into a more advanced topic. So let's neglect for now critical fracture growth to be toughness. Okay, and just to give you a preview of what this toughness is, we'll not go in detail about this right now, but toughness or intensity is as the limit of the product of two quantities, specifically is a limit of distance from the tip times stress as you get closer to the tip. So again, we're not going to talk in detail about this today, but we will on Wednesday. But the intensity, stress intensity factor, is just a product of length and stress. And for these solutions of linear elastic fracture mechanics, when you make that product, instead of getting a value which goes to infinity close to the tip, you just get a value which is fine and it's not infinity. Okay, so do you guys have any questions? Well, if not, then we'll continue on Wednesday. Thank you, guys.
I have a related question.
Okay.